Hello and welcome. Tonight, we'll be exploring a question that sounds almost simple at first. Will humanity ever reach another galaxy? After all, when you look up on a clear night, the universe can seem strangely close. Stars shimmer above you. A pale band of the Milky Way stretches across the darkness. Somewhere in that same sky, far beyond the stars we can see with our eyes, enormous galaxies are drifting through space. They look like neighbors, but they are not. The night sky hides something from us. It hides depth. So, find a comfortable place to rest, and let's gently begin our journey into one of the most fascinating questions in science. Imagine yourself standing outside on a quiet night. Perhaps the air is cool. Perhaps there is a faint breeze moving through the trees. Above you, the sky is dark and almost perfectly still. You look upward. There are thousands of points of light. Some are stars. Some of the faintest patches of light are distant galaxies. And yet, to your eyes, they all seem to occupy the same enormous surface overhead. It is almost as though the universe were painted onto a dark ceiling. But that ceiling does not exist. There is no flat surface holding the stars in place. Instead, there is an immense depth extending away from you in every direction. And this is where our intuition begins to fail. Human beings are very good at understanding distances that matter to everyday life. You can look at a tree and estimate whether it is 10 meters away or 50. You can see a mountain and understand that it is farther away than the house in front of you. Your brain uses perspective, shadows, movement, and countless other visual clues to construct a sense of depth. But the night sky offers almost none of those familiar clues. A star a few dozen light-years away and a galaxy millions of light-years away can both appear as tiny points of light. They can even appear close together in the sky, while being separated by an almost unimaginable distance. Two distant lights on different roads might look as though they are sitting beside one another when seen from far away. The universe does something similar. Two galaxies can appear close together simply because they happen to lie in almost the same direction from Earth. Their apparent closeness tells us very little about how far apart they actually are. And there is an even stranger possibility. A single point of light may hide something enormous. What looks like a tiny speck might be one star, but another tiny speck, apparently no larger, might be an entire galaxy containing hundreds of billions of stars. Our eyes cannot simply look at a point of light and feel the scale behind it. The light reaches us. We see the point, but the enormous distance that the light has crossed remains invisible. It is almost like receiving a small photograph through the mail without knowing how far the envelope has traveled. The message arrives. The journey remains hidden. This is why the night sky can feel peaceful and familiar, while secretly representing distances that are almost impossible to imagine. The stars seem close enough to touch. The galaxies seem like faint decorations scattered among them. But behind that beautiful simplicity is a universe extending through 3 dimensions, with enormous regions of darkness between its islands of light. And our own location is only one small part of that structure. We live on Earth. Earth travels around the Sun. The Sun is one ordinary star among hundreds of billions in the Milky Way. The Milky Way is one galaxy among many, and the Milky Way itself belongs to a small gravitational neighborhood of galaxies known as the local group. The farther outward we zoom, the less special our cosmic address becomes. Earth is home. The solar system is our neighborhood. The Milky Way is our galaxy. And beyond it is an immense cosmic landscape filled with other galaxies, other stars, and enormous spaces between them. This is important because before we ask whether humanity can travel to another galaxy, we need to correct one simple misunderstanding. The galaxies were never as close as they look. The sky has compressed their enormous 3-dimensional distances into a beautiful 2-dimensional scene. And once we begin restoring that missing depth, the scale of the problem changes completely. Consider Andromeda. It is our nearest major galactic neighbor, roughly 2.5 million light-years away. That phrase can sound almost harmless, 2.5 million, but a light-year is the distance light travels in 1 year, so even light, the fastest known messenger in the universe, needs about 2.5 million years to cross the distance between us and Andromeda. The light entering your eyes when you look toward that galaxy began its journey unimaginably long ago. It left Andromeda before modern human civilization existed, before written history as we know it, before our ancestors looked up at the same sky and understood that those distant points were other galaxies. The light has been traveling all that time, and only now does it arrive. So when you look toward Andromeda, you are not seeing the galaxy exactly as it exists at this moment. You are seeing an ancient version of it. The universe is filled with these delayed messages. Every distant galaxy is telling us something about its past. The farther away it is, the farther back in time we are looking. A telescope, then, is not simply a device for seeing farther, it is also a device for seeing earlier, and that gives the night sky a second dimension that our eyes do not immediately recognize. There is the space between us and the stars, and there is the time contained inside the light that crosses that space. For now, we can simply let that thought settle quietly. Above you, the sky still looks almost flat, but it isn't. Behind every point of light is depth. Behind every distant galaxy is time. And between those galaxies lies an emptiness so vast that even light needs millions of years to cross it. So before humanity can ask how to build a spacecraft capable of reaching another galaxy, we first have to understand what it would actually mean to cross the distance between two of these cosmic islands. Because Andromeda is not merely far away. In cosmic terms, it is one of our closest neighbors, and if our nearest major neighbor is already separated from us by millions of years of light travel, then the true journey between galaxies is only beginning to reveal itself. When we hear that Andromeda is about 2.5 million light-years away, the number can almost float past us without meaning much. 2.5 million. It is simply too large for everyday intuition. So instead of trying to imagine the entire number at once, let us slow down and think about what a light-year actually means. A light-year is a distance. It is the distance light travels in 1 year. And light moves extraordinarily quickly. In empty space, it travels at almost 300,000 kilometers every second. Every second. So when we say that Andromeda is about 2.5 million light-years away, we are saying that even something traveling at the fastest speed known to nature would need roughly 2.5 million years to cross that distance. And this is our nearby galactic neighbor. That is the part worth remembering. Andromeda is not some impossibly distant galaxy at the edge of everything we can see. It is one of the galaxies closest to us on the grand cosmic map. Yet between us and it lies an expanse so enormous that ordinary words like far begin to lose their meaning. Imagine standing on a quiet shore and looking toward an island. You can see the island. Perhaps you can even make out a few details along its coastline. But imagine that the ocean between you and that island is so wide that a signal traveling at the speed of light would need millions of years to cross it. That is closer to the scale we are dealing with. And even this comparison is gentle. The ocean on Earth is filled with water, life, ships, islands, weather, and countless things to encounter along the way. Intergalactic space is radically different. Between galaxies, matter becomes extraordinarily sparse. There are still particles and fields, of course. Space is not a perfect, absolute nothingness, but compared with the density of matter we experience around us, the spaces between galaxies are extraordinarily empty. There are no convenient ports waiting between the stars. No cosmic roads with service stations every few thousand kilometers. No natural sequence of resting places where a spacecraft could stop, repair itself, and continue. A spacecraft crossing intergalactic space would spend an enormous part of its journey surrounded by darkness and extremely thinly distributed matter. And this changes the nature of the problem. It is tempting to think of intergalactic travel as simply a longer version of space travel. Earth to the moon to Mars, Mars to somewhere farther away. Just keep going. But the distances between galaxies are not merely larger versions of the distances between planets. They belong to a completely different scale. The moon is about 1¼ light seconds from Earth. Light can cross that distance in little more than a second. The Sun is about 8 light minutes away. The nearest stars are several light years away, and Andromeda is roughly 2.5 million light years away. The scale expands so quickly that our familiar mental map simply breaks apart. And there is another strange thing about this distance. We can see Andromeda. We can observe it with telescopes. We can study its shape. We can examine the light arriving from it. We can learn about its stars and the enormous structure of the galaxy. Yet none of this means that we are seeing Andromeda as it is right now. We are seeing light that left it millions of years ago. Imagine sending a letter to someone on the other side of the world. By the time they receive it, the world may have changed a little. Perhaps the weather is different. Perhaps they have moved to another house. Perhaps a tree outside their window has grown. But with Andromeda, the delay is not measured in days or months. It is measured in millions of years. The message we receive today began its journey before modern human beings had built cities and civilizations. The galaxy we see is therefore a historical record. Its light is an old message arriving late. And every time we look farther into space, we also look farther backward in time. This is one of the quiet miracles of astronomy. The universe does not need to bring its distant past to us in a time machine. It has been sending the past toward us all along. Photons leave distant stars and galaxies, travel through darkness for immense stretches of time, and eventually arrive at Earth. A telescope simply gives us a better way to receive those messages. But receiving a message is very different from traveling to the sender. That distinction will become increasingly important, because if the light from Andromeda needs millions of years to reach us, imagine trying to send something much slower than light in the opposite direction. Imagine a spacecraft. Imagine people inside it. Imagine machines that must continue working, life support systems that must remain reliable, supplies that must remain available, and generations of human beings who may be born long after the original crew has disappeared. Suddenly, the distance is no longer just a number. It becomes a duration, and duration becomes a problem of survival. A spacecraft does not merely need to reach its destination. It needs to remain a functioning spacecraft while traveling there. For a short mission, this is already difficult. For a journey measured in thousands or millions of years, almost every assumption we make about engineering begins to change. A machine can fail. A component can wear out. Radiation can damage electronics and biological tissue. Energy systems must continue functioning. Materials must withstand enormous periods of time. And if human beings are aboard, there is an even greater question. Can a human society survive a journey longer than recorded civilization has existed? Perhaps the passengers would need to become several generations. Children would be born inside the spacecraft. They would grow up knowing the stars not as places humans visit, but as distant points outside their windows. Their children would inherit the same journey, and their children would inherit it again. Eventually, the original destination might become almost mythical. The people who launched the mission would have become ancestors separated from the travelers by thousands of generations. At that point, we would no longer really be talking about a spacecraft crossing space. We would be talking about a civilization moving through space. And yet, perhaps there is another possibility. Perhaps we could make the journey much faster. Perhaps instead of traveling at the speeds of our current spacecraft, we could somehow reach a significant fraction of the speed of light. This is where the story becomes even stranger, because at first, increasing speed seems like the obvious answer. If the distance is too large, simply go faster. But the universe has placed a remarkable limit on how far that idea can take us. The closer a massive object gets to the speed of light, the more difficult it becomes to accelerate it further. The energy requirements become increasingly extreme, and the exact speed of light itself is not simply another milestone waiting for a sufficiently powerful engine. For anything with mass, reaching the speed of light is forbidden by our current understanding of relativity. So perhaps the question is not, how powerful can we make our engines? Perhaps the deeper question is, how close to the universe's ultimate speed limit could we ever travel? And that question leads us naturally into one of the strangest discoveries in modern physics. Because once you begin moving close enough to the speed of light, something unexpected happens. The journey does not only change for the spacecraft, it changes for time itself. And that is where our ordinary understanding of a journey begins to dissolve. There is something humbling about Voyager 1. It is one of the farthest human-made objects ever sent away from Earth, carrying with it a small piece of our technological history. It has traveled far beyond the familiar planets, continuing outward into the darkness of interstellar space. And yet, if we place Voyager beside the distance to another galaxy, its journey suddenly becomes almost unimaginably small. Voyager moves at roughly 17 kilometers per second. That is an extraordinary speed for a spacecraft. But the universe has a strange way of making extraordinary things look small. At that speed, reaching Andromeda would take tens of billions of years. Not thousands, not millions, tens of billions, longer than the age of the universe as we currently understand it. And this is where the scale of intergalactic travel becomes difficult to absorb. A spacecraft can be fast. A spacecraft can travel farther than any human being has ever traveled. It can leave the planets behind and continue into a region of space where the sun becomes just another distant star. But none of that changes the enormous distance between galaxies. It is a little like crossing a small pond and then discovering that what you thought was the opposite shore was actually another continent. You can make your boat faster. You can make it stronger. You can improve its navigation. But the fundamental scale of the journey remains. And so, naturally, we might ask a simple question. What if we build a much faster spacecraft? Perhaps 17 kilometers per second is simply too slow. What if we could somehow reach 10% of the speed of light? That would be astonishing by human standards. At 10% of light speed, a spacecraft would travel at a speed that makes today's spacecraft seem almost motionless by comparison. And yet Andromeda would still be roughly 25 million years away in the Earth's frame of reference. 25 million years. It is difficult to imagine a human life lasting that long. So instead, imagine a civilization. Imagine cities changing, languages changing, continents slowly changing, species appearing and disappearing, the Earth itself passing through enormous geological transformations. And somewhere out in the darkness, the same spacecraft is still moving toward its destination. This is the strange lesson hidden inside the numbers. Increasing speed helps enormously, but distance on the scale of galaxies is so extreme that even extraordinary speed can leave us with extraordinary travel times. Perhaps we could go faster still. Imagine reaching half the speed of light. The journey becomes shorter, but it is still measured in millions of years from the perspective of Earth. Imagine going even faster, 9/10 of the speed of light. Now we have entered a regime where ordinary intuition becomes even less useful, because something else has changed. Not the distance between the galaxies, not the vastness of space, but the way time passes. This is where Einstein's theory of relativity enters our story. We often imagine time as a universal clock hanging somewhere above the universe. 1 second for you, 1 second for me, 1 second for a spacecraft moving through the darkness. But nature does not work quite that way. Time is woven together with space, and when objects move at speeds approaching the speed of light, different observers can measure different amounts of elapsed time. This is called time dilation. The phrase sounds technical, but the basic idea can be approached gently. Imagine two people carrying clocks. One remains on Earth, the other travels aboard a spacecraft moving extremely fast. When the traveler eventually returns, the two clocks may not agree about how much time has passed. The difference can become enormous when the spacecraft travels sufficiently close to the speed of light. For the traveler, the journey can take much less time than it does for people who remain behind. This sounds almost like a loophole. Perhaps the universe has given us a way around the enormous duration of intergalactic travel, and, in a sense, it has, but only for the traveler. The distance has not vanished, the galaxy has not suddenly moved closer, the universe has not folded itself into a smaller room. Instead, the traveler experiences the passage of time differently. From Earth, millions of years might pass. For the traveler, much less time could pass. This distinction is important. Time dilation does not mean that we can simply ignore the distance between galaxies. It means that space and time are connected in a way our everyday experience does not prepare us to imagine. And there is something deeply strange about what this would mean for a human being. Suppose, in some far future, humanity develops a spacecraft capable of traveling extremely close to the speed of light. Suppose the engineering problems are somehow solved. Suppose the spacecraft can protect its passengers from radiation, collisions with tiny particles, and the enormous demands of accelerating to such a speed. The travelers leave Earth. From their perspective, the journey may be surprisingly short compared with the time measured on Earth. But when they return, Earth may be almost unrecognizable. Their friends would be gone, their families would be gone, the cultures they knew might no longer exist. The languages could have changed, the political boundaries could have disappeared, entire civilizations could have risen and fallen. The traveler would not simply have traveled across space, they would have traveled into Earth's future. In this sense, relativistic travel carries a strange price. You can save time for yourself while giving up your connection to your own era. And perhaps that is one of the most unsettling aspects of interstellar and intergalactic travel. The hardest part may not always be surviving the journey. It may be arriving. Imagine stepping out of a spacecraft after what felt like a manageable portion of your life, only to discover that the world you left behind belongs to history. The stars would still be above you. The laws of physics would still be the same. But almost everything familiar could have disappeared. And if the destination is another galaxy, there is another problem: communication. Even if a spacecraft could travel at an enormous fraction of the speed of light, ordinary conversation between Earth and the travelers would still be painfully slow. A message sent toward Andromeda would take millions of years to arrive. A reply would require millions of years more. There would be no ordinary telephone call, no live video, no casual message saying, "How is everything going?" A question could be sent by one generation and answered by descendants who had never met the person who asked it. The distance between civilizations would therefore become a distance between eras. This is another reason intergalactic travel is unlike any journey humans have experienced. We normally imagine a journey as a temporary interruption. You leave home, you travel, you arrive, and eventually you return. But on intergalactic scales, the word journey begins to lose its familiar meaning. A journey can become a historical epoch. A spacecraft can become an inheritance. A mission can outlive the civilization that launched it. And a traveler can arrive in a future that no longer remembers why the journey began. Yet relativity still gives us something remarkable. It tells us that the universe does not treat time as an absolute background. Time can stretch. Time can pass differently. The faster you move, the more profound this effect becomes. But there is still a boundary. The speed of light remains fundamental. A massive spacecraft cannot simply accelerate until it reaches the same speed as light. The closer it gets, the more difficult further acceleration becomes. The energy required rises dramatically. And so, even with the extraordinary possibilities offered by relativity, the universe does not hand us an easy escape. Instead, it gives us something more subtle. It allows time itself to become part of the journey. And this leaves us with a strange thought. Perhaps the question is not simply how fast humanity can travel through space. Perhaps we also need to ask what happens to humanity when the journey becomes so long that space and time can no longer be separated. Because while we are trying to cross the universe is not standing still. Space itself is changing, and that means our destination may not be waiting patiently for us. The cosmos is moving too. There is a quiet moment in every journey when you begin to realize that distance is not the only thing you are carrying. You are carrying time. For a traveler moving across a city, this hardly seems important. You leave home, cross a few streets, perhaps sit beside a window for a while, and eventually arrive. The clock on your wrist and the clock on the wall seem to agree. 1 minute passes, then another. Nothing about this feels mysterious. But the universe becomes very different when the journey approaches the speed of light. At those speeds, time itself can no longer be treated as though it were the same for everyone. This is one of the central discoveries of Einstein's theory of relativity, and it leads to a strange possibility. A journey that takes an enormous amount of time for people watching from Earth can take much less time for the people making the journey. It sounds almost like science fiction, but the effect is real. It is called time dilation. To understand the basic idea, imagine 2 clocks. One clock stays quietly on Earth. The other travels aboard a spacecraft moving at an extremely high speed. When the spacecraft eventually returns, the 2 clocks may no longer agree about how much time has passed. The clocks have not malfunctioned. Neither one is broken. They have simply experienced different paths through space-time. For ordinary speeds, the difference is far too small for us to notice in daily life. When you walk to the kitchen, drive to work, or fly across an ocean, the effect exists in principle, but it is tiny. You do not feel time stretching around you. You do not notice your breakfast lasting a fraction of a fraction longer than it would for someone standing still. But as the speed of the spacecraft approaches the speed of light, the effect becomes increasingly important. The traveler experiences less elapsed time than someone who remains behind. And suddenly, the enormous distance to another galaxy takes on a new meaning. Suppose a future civilization somehow builds a spacecraft capable of traveling extremely close to the speed of light. The spacecraft leaves Earth. From Earth's perspective, the destination remains millions of light years away. The journey still unfolds across an enormous span of cosmic history. But aboard the spacecraft, the travelers can experience a much shorter amount of time. This is one of the most beautiful and counterintuitive ideas in modern physics. The universe does not have one universal clock ticking in the background. There is no enormous cosmic clock hanging above the stars, counting identical seconds for every observer everywhere. Instead, time is part of the fabric of the universe. Space and time are connected, and motion changes how different observers measure them. We can imagine space-time as something like a vast landscape. 2 travelers can take different paths across that landscape and experience different amounts of elapsed time. The analogy is imperfect, but it gives us a gentle way to approach the idea. And this is where intergalactic travel becomes especially strange. Imagine that you are one of the travelers. You enter the spacecraft. The doors close. The engines begin to accelerate. the Earth slowly disappears behind you. At first, nothing about the experience needs to feel extraordinary. You are simply leaving. But as the spacecraft approaches an enormous fraction of the speed of light, the relationship between your time and the time on Earth begins to diverge more strongly. For you, the journey might eventually feel surprisingly short compared with the millions of years measured by someone who remains behind. But there is an important detail that we must not lose. Time dilation does not make the galaxy physically closer. Andromeda does not suddenly move next door. The distance has not been erased. You have not discovered a secret tunnel through space. Instead, your measurement of the journey changes because your path through space-time is different. This distinction is crucial. It is easy to hear about time dilation and imagine that relativity has somehow defeated the enormous distances between galaxies. It has not. Relativity gives us a remarkable way to understand how time and distance are connected. But it does not give a massive spacecraft permission to travel faster than light. The speed of light remains a fundamental limit in our current understanding of physics. As a spacecraft with mass approaches that limit, the energy required to accelerate it further becomes extraordinarily large. The closer you try to get, the more difficult the final approach becomes. So even if a future civilization became unimaginably advanced, it could not simply press a button and make a massive spacecraft reach the speed of light. Nature does not seem to offer that shortcut. Still, time dilation creates an extraordinary possibility. Imagine a traveler who leaves Earth at a speed extremely close to the speed of light. The traveler might experience years, or perhaps decades during a journey that, from Earth's perspective, corresponds to a vastly longer period. But when the traveler looks back toward home, something profound has happened. Earth has moved into the future, not metaphorically, literally. The traveler has aged less than the people who remained behind. And this means that near light speed travel can act, in a sense, like a one-way journey into the future. You leave one era, you arrive in another. The strange part is that the traveler does not need to experience all the years that pass on Earth. Those years simply pass for everyone else. Imagine leaving your home when you are 30 years old. You travel for what feels like a manageable portion of your life. Then you return. You are older, but Earth may be separated from the moment you left by centuries, thousands of years, or far more, depending on how the journey was designed. The people you knew would be gone. The buildings you remember might no longer exist. The languages could have changed. The cultures could have transformed into something completely unfamiliar. The night sky itself could look different. And yet, from your own perspective, you may not have experienced all of that time. This is where the romance of relativistic travel begins to meet something much more human. Physics may allow you to reduce the amount of time you personally experience during an enormous journey, but it cannot preserve the world you left behind. You can save your own time, you cannot save everyone else's, and that may be one of the deepest costs of traveling between galaxies. The distance is not only between two places, it is between two moments in history. There is another consequence: communication. Imagine sending a message from Earth to Andromeda. Even light requires roughly 2.5 million years to cross that distance. So there can be no ordinary conversation, no live video, no quick exchange, no moment when someone on Earth asks a question and waits for an answer over dinner. A message could leave Earth. Millions of years could pass. Only then would the message arrive. And if the recipient replied immediately, millions of years would pass again before the answer returned. The conversation would last longer than entire human civilizations. One person might send a message. Their distant descendants might receive the answer, and those descendants might no longer understand why the question was asked. The universe turns communication into history, and this reminds us of something important. Light does not merely show us distant places. It separates moments in time. Every distant observation is delayed. Every message has a travel time. Every attempt to communicate across the cosmos is also an attempt to bridge two different moments. Now imagine the spacecraft continuing toward another galaxy. The travelers are moving extremely fast. Their clocks are running differently from the clocks on Earth. But while they are making this extraordinary journey, something else is happening. The universe around them is not frozen. Space itself is expanding. Galaxies are changing their large-scale separations. The cosmic landscape is evolving. So even after we understand time dilation, another question remains. What happens when the destination itself belongs to an expanding universe? Because perhaps the most difficult thing about crossing cosmic distances is not that the road is long. Perhaps it is that the road itself is changing while we travel. And beyond a certain scale, the universe may not simply make the journey difficult. It may make some destinations impossible to reach at all. There is something we often forget when we imagine a journey across space. We imagine the destination waiting patiently for us. A star sits over there. A galaxy sits over there. The distance between us is simply an empty stretch of space. All we have to do is cross it. But the universe is not a frozen room. Space itself is changing. The galaxies are not arranged inside some enormous, motionless container that has existed unchanged forever. On the largest scales, the universe is expanding. And once we understand this, the idea of traveling to another galaxy becomes even more interesting. Imagine a loaf of bread slowly rising in an oven. Before the dough expands, two small marks on its surface might be relatively close together. As the dough rises, the distance between those marks increases. Neither mark needs to be running across the surface. The space between them is changing. This is only an analogy, of course, but it gives us a gentle picture of what cosmologists mean when they talk about the expansion of the universe. Another familiar image is a balloon. Imagine drawing several small dots on its surface. Now imagine the balloon slowly expanding. As the surface stretches, the dots become farther apart. From the perspective of any one dot, the others appear to move away. There is no single dot that has to be the center of the expansion. The important idea is that the space between distant regions changes. The real universe is far more complicated than a balloon or a loaf of bread. But the analogy helps us step away from the picture of space as an empty, unchanging room, because it is not. And this matters enormously when we think about intergalactic travel. For nearby galaxies, gravity can be powerful enough to overcome the general expansion of space. Our Milky Way and Andromeda are gravitationally connected as members of the same local group. They are not simply drifting away from one another as though they were dots painted on an enormous balloon. In fact, Andromeda and the Milky Way are moving toward a future encounter. So we need to be careful. Cosmic expansion does not mean that every galaxy is moving away from every other galaxy in exactly the same way. On smaller scales, gravity can gather matter together. It can bind stars into galaxies. It can bind galaxies into groups and clusters. But when we step back far enough, the expansion of the universe becomes the dominant feature. And the farther we look, the more important this large-scale expansion becomes. This creates a strange situation. Imagine that you are preparing a spacecraft for a journey to an extremely distant galaxy. You calculate the distance, you calculate the speed, you calculate how much time the trip will require. You build your spacecraft, you launch. But while you are thinking about the distance, the universe itself is changing the distance. The destination is not simply sitting at a fixed coordinate on a cosmic map. The map itself is evolving. This does not mean that the expansion of the universe behaves like a wind pushing galaxies through space. That picture is too simple. Instead, the geometry of space changes on the largest scales. and the effect becomes increasingly important over enormous distances. This is one reason the universe cannot be understood simply as a giant collection of objects moving around inside an otherwise unchanging background. The background matters, space matters, the history of the universe matters, and even the apparently empty regions between galaxies matter. When astronomers map the large-scale universe, they discover something beautiful. Galaxies are not scattered randomly like grains of sand. They form enormous patterns, long filaments, dense clusters, sheets and strands stretching across unimaginable distances. Between these structures are vast regions containing comparatively little matter. Astronomers call this arrangement the cosmic web. It is one of the largest structures we know, and it gives us another way to imagine the universe. Instead of thinking of galaxies as isolated islands floating randomly in darkness, imagine an enormous web stretching across space. Galaxies gather along its threads. Clusters form where several threads meet, and between them are immense cosmic voids. These voids are not perfectly empty. There can still be thin gas, dark matter, radiation, and other components of the universe within them. But compared with the dense regions where galaxies gather, they are remarkably sparse. The universe is therefore not simply full, it is structured. There are crowded places, there are quiet places, there are enormous bridges of matter, and there are stretches of cosmic emptiness. One of the invisible ingredients helping shape this structure is something called dark matter. The name can sound mysterious, but the basic idea is surprisingly simple. Astronomers observe the gravitational effects of matter that does not appear to interact with light in the ordinary way. We cannot simply point a telescope at dark matter and see it glowing. Instead, we infer its presence from what its gravity does. It helps provide the gravitational scaffolding around which large cosmic structures can form. Imagine seeing a city at night from far above. You might not be able to see every road, but you could see where the lights gather. You could trace the shape of neighborhoods. You could infer the underlying structure from the patterns. Dark matter is somewhat like that. We do not see it directly through ordinary light, but we see the gravitational fingerprints it leaves on the cosmic landscape. And then there is another component of the universe with an entirely different role: dark energy. The name is often misunderstood. It does not necessarily mean a mysterious substance rushing through space like an invisible wind. Instead, dark energy is the name associated with whatever is responsible for the observed accelerated expansion of the universe. We do not yet have a complete understanding of its underlying nature, but its large-scale effect is clear. The expansion of the universe is accelerating, and that changes the long-term story of cosmic travel. Because if the universe continues expanding in the way current observations suggest, some distant regions will become increasingly separated from us. The universe does not simply give us a bigger map, it changes the map over time, and eventually, something extraordinary can happen. There can be galaxies whose ancient light is still reaching us, allowing us to see them. But because of cosmic expansion, signals sent from us today may never be able to reach those regions. This is where the distinction between seeing something and reaching it becomes profound. You might look toward a distant galaxy and receive its ancient light. You might study its stars. You might measure its motion. You might learn about its history. And yet, a spacecraft leaving Earth today could face a future in which that galaxy is no longer physically accessible. The galaxy is visible. But visibility is not the same thing as reachability. This is one of the most important ideas in the entire journey we are taking tonight. The universe can show us something without promising that we can ever visit it. And once we understand that, intergalactic travel stops being merely a question of better engines. It becomes a question about the structure of the universe itself. There are distances that technology might one day challenge. There are speeds that engineering might one day approach, but there are also limits written more deeply into the cosmic landscape. Limits created not by the weakness of our machines, but by the way space and time behave. And beyond those limits, the word far begins to mean something very different. Because some places are not simply far away, they may be beyond the reach of any signal we could ever send. And that brings us to one of the strangest boundaries in the universe, a boundary that is not a wall, not a border, not a glowing line across the darkness, but a limit on what can ever influence what, a cosmic horizon. There is a difference between seeing a place and being able to reach it. On Earth, we rarely have to think about this distinction. You can see a mountain in the distance, and if there is a road leading toward it, you can imagine eventually standing on its slopes. You can see an island across the water and, at least in principle, build a boat and cross the distance. Even when a place is difficult to reach, we usually assume that the obstacle is practical. Perhaps the road is too long, perhaps the ocean is too rough, perhaps we need a better vehicle. But the universe introduces a much stranger possibility. There may be places we can see that we can never reach, not because our engines are too weak, not because we have not invented the right fuel, not because the journey would simply take too long, but because the structure of space-time itself can prevent a future connection. To understand this, let us return to something we have already encountered: light. Light is extraordinarily fast. It is the fastest known way information can travel through ordinary space. When we look at a distant galaxy, we are receiving information carried by light. But light still needs time. That means there is a limit to how much of the universe we can observe. The universe has existed for a finite amount of time, and information cannot travel infinitely fast. So there are regions of the cosmos whose light has not had enough time to reach us. The region from which information has had time to reach us is what we call the observable universe. The word observable is important. It does not mean that this is necessarily the entire universe. It means that this is the part from which information has been able to reach us during cosmic history. Beyond that boundary, there may be much more universe. We simply cannot see it from our present location. It is a little like standing on a dark coastline at night. You shine a lamp into the distance. The light illuminates only a certain region. Beyond that region, you cannot tell what is there. But the darkness does not mean there is nothing beyond it. It means information from there has not reached you. The cosmic situation is much more profound. Instead of a small lamp, imagine the entire history of the universe sending light outward. Some light has reached Earth. Some is still traveling, and some regions are simply too distant for their information to have arrived. This creates one kind of cosmic boundary. But there is another boundary that is even more surprising. The universe is expanding, and its expansion is accelerating. Because of this, there are regions of space that can become separated from us so rapidly on the largest scales that light sent from them today may never reach us. This gives rise to the idea of a cosmic event horizon. The phrase sounds dramatic, but there is no glowing line floating in space, no wall, no invisible fence, nothing a spacecraft could bump into. It is better to imagine it as a limit in the future, a boundary created by the combined behavior of expanding space and the finite speed at which information can travel. Beyond this boundary, certain future signals can never make the journey to us, and this changes the meaning of distance. Imagine two islands separated by an ocean. Normally, if the ocean stays still, a faster ship can simply cross it more quickly. But now imagine an ocean whose water between the islands is continuously stretching. The farther you try to sail, the more the distance changes. At some point, the stretching can become so strong that a ship traveling within the rules of the ocean can never close the gap. Again, the universe is not literally an ocean, but the analogy helps us feel the difference between an ordinary engineering problem and a fundamental limit. If a spacecraft is too slow, we can imagine building a faster spacecraft. If it does not have enough fuel, We can imagine developing a better energy source. But if the geometry of space-time prevents a future connection, there may be no engine to invent. This is where the idea of causality becomes important. Causality is simply the relationship between events that can influence one another. A signal leaves one place, it travels, it arrives somewhere else. The arrival can then affect what happens there. That chain of influence is part of the structure of physical reality. But the universe does not allow arbitrary events to influence one another. The speed of light places a fundamental limit on how information can propagate through space-time, and cosmic expansion can make that limit even more consequential. A region may be visible to us because we are receiving ancient light from it, yet a new message sent from Earth today may never reach the same region. This sounds contradictory at first. How can we see something that we can never reach? The answer lies in time. The light we see began its journey long ago. The universe was in a different state then. The geometry and expansion of space were different. That ancient light has been traveling toward us for an enormous span of cosmic history. But if we send a new signal today, it begins its journey under the conditions of the universe as it exists now. And the future can be very different from the past. This is one of the most beautiful and unsettling ideas in cosmology. We can receive an ancient message from a place without being able to send a new message back. We can see the past of a galaxy while being separated from its future by cosmic expansion. In that sense, astronomy gives us a strange privilege. We can look at places that may already be slipping beyond our future reach. The photons arriving tonight could have been traveling for billions of years. They are telling us about a universe that existed long before our civilization, but the galaxy itself has continued evolving during all that time. The object we see through our telescope is not frozen in the moment represented by its light. It has continued moving. Its stars have continued forming and dying. Its structure has continued changing. And the light we receive is simply the portion of that history that has finally reached us. This is why astronomers often speak about looking back in time when they observe distant galaxies. The farther away we look, the older the light tends to be. And as telescopes become more sensitive, we can observe galaxies from earlier and earlier periods of cosmic history. We are effectively opening older and older pages in a cosmic book. But there is no guarantee that every page we can read is a place we could ever visit. A photograph of a distant island does not mean we have a boat capable of reaching it. In the same way, an image of a distant galaxy does not mean a spacecraft launched today could establish contact with it. This distinction is easy to overlook because our brains are accustomed to a much smaller world. On Earth, seeing usually implies accessibility. If you can see the mountain, there is probably a path. If you can see the coastline, there is probably a way to reach it. But the universe does not promise that. The cosmos can reveal something without offering a route to it. And this is where the question of intergalactic travel becomes much deeper. Perhaps the greatest obstacle is not technology. Perhaps the universe itself determines the limits of our cosmic neighborhood. There may be galaxies that future civilizations could approach with sufficiently advanced technology. There may be others that become unreachable because cosmic expansion carries them beyond our causal horizon. And there may be regions of the universe that we will never see at all. These are different kinds of boundaries. Some are technological, some are temporal, some are cosmological, and the most profound of them cannot be solved by simply building a more powerful rocket. No amount of fuel changes the age of the universe. No stronger engine changes the finite speed of light. And no spacecraft can simply command expanding space-time to stop. The thought can feel strangely quiet. There is no villain here, no catastrophe, no wall constructed to keep humanity out. Only the natural architecture of the cosmos. The universe does not need to forbid us from visiting every galaxy. It only needs to follow its own laws, and those laws may leave humanity with a peculiar kind of freedom. We may be unable to travel everywhere, but we can still look, we can still measure, we can still listen to the ancient light arriving from across the darkness. And perhaps that is where our story takes its next turn, because if physical travel has limits, information does not stop being meaningful. Every photon that reaches a telescope is carrying something across the universe. A message about stars, a message about motion, a message about chemistry, a message about time, and with the right instruments we can learn to read it. Perhaps the universe has already been bringing distant galaxies to us, not as places we can stand upon, but as stories written in light. And the next question is whether that kind of journey might be enough. There is a quiet irony hidden inside everything we have discovered so far. We have spent so much time asking how humanity might travel to another galaxy. How powerful would the spacecraft need to be? How fast could it go? How long could people survive? Could time dilation help? Could we somehow cross the enormous distances created by the expanding universe? And yet, while we have been asking all of these questions, something has already been traveling between the galaxies. Light. It has been traveling for millions and billions of years. It crosses the darkness without needing a spacecraft. It carries information without carrying passengers. And when a small portion of that ancient light finally reaches Earth, we can collect it, we can study it, we can learn from it. In a sense, the universe has already been sending us its distant places. We simply had to learn how to listen. Imagine a photon leaving a distant star. We do not need to think of it as a tiny glowing ball flying through space. It is better, for our purposes tonight, to think of it as a messenger. It begins its journey in a distant region of the cosmos. Then it travels. For an immense amount of time, it crosses the darkness between galaxies. Nothing about the journey needs to be dramatic. There is no road, no engine, no destination marker, only the quiet propagation of light through space. Eventually, some of that light reaches Earth, and if it happens to enter a telescope, it becomes part of human knowledge. This is one of the reasons telescopes are so extraordinary. A telescope does not merely allow us to see something faint. It allows us to receive information that has traveled farther than any human-made object could ever travel. The photons arriving from a distant galaxy have crossed a distance our spacecraft could not realistically cross. They have done the journey for us, and they bring information with them. Not information in the form of words, not a message written by an alien civilization. Something subtler. Light itself carries clues about the physical conditions of the universe. Its wavelength can change. Its patterns can reveal motion. Its spectral features can tell us about the elements present in stars and galaxies. Its brightness can help astronomers understand distances and energetic processes. Its shape and distribution can reveal enormous structures. The faint light from a distant galaxy is therefore much more than a picture. It is evidence, it is data, it is a record of physical events that happened long before the light reached us. Imagine standing in a quiet room and hearing a sound from far away. You cannot see what created it, but from the sound, you may learn something about the source. Perhaps you can recognize the difference between a bell and a voice. Perhaps you can tell whether the sound is approaching or moving away. Perhaps the sound has traveled through an environment that changes it before it reaches you. Astronomy works in a somewhat similar spirit. We cannot stand beside most distant galaxies, but we can study the light that arrives from them, and from that light, we reconstruct what happened. This is one of the great transformations created by science. Humanity learned that observation does not require physical contact. We do not need to touch a star to study it. We do not need to land on another galaxy to learn what its stars are made of. We do not need to travel across a cosmic void to discover how galaxies move. We can measure the light, and light has been crossing the universe for us. Consider what happens when astronomers spread distant starlight into its different wavelengths. The light can reveal characteristic patterns associated with different elements. In a very real sense, the light allows us to study the chemistry of objects that are unimaginably far away. Hydrogen, helium, oxygen, iron, and many other elements leave distinctive signatures. The atoms themselves do not need to travel from the distant galaxy to our laboratory. Their fingerprints arrive in the light. This is an extraordinary idea. A star can be millions of light years away. We cannot touch it. We cannot scoop material from its surface. We cannot bring a piece of it home. And yet we can learn about what it is made of. The universe allows us to study distant objects remotely because light carries traces of their physical state. We can also learn about motion. When a galaxy moves relative to us, the wavelengths of its light can shift. This is connected to the familiar idea of redshift. Again, the name is less important than the picture. Imagine a sound changing as a vehicle moves away from you. The pitch shifts. Light has its own version of this kind of change. Its wavelengths can be stretched when the source and observer are separated by motion and, on cosmic scales, by the expansion of space. That stretching gives astronomers another clue about the universe. It tells us that distant galaxies are not simply static dots painted on the sky. They are part of a dynamic cosmos. They move, they evolve, they form stars. Stars die. Galaxies interact. Structures grow. And all of this information can reach us through light. The farther we look, the farther back in cosmic history we see. This is why the night sky can be thought of as a kind of natural archive. Imagine a library whose books are not arranged on shelves but arrive as beams of light. Nearby books contain relatively recent chapters. Farther books contain older chapters. And the most distant observations can reveal conditions from very early in cosmic history. Astronomers can therefore use distant galaxies to reconstruct how the universe changed over time. They can study galaxies at different stages of development. They can compare younger-looking systems with more mature ones. They can examine the growth of large-scale structures. They can investigate how stars formed and how galaxies changed. None of this requires humanity to physically travel between galaxies. The information comes to us. And this gives us a new way to think about exploration. Perhaps exploration does not always mean arriving. Perhaps exploration can also mean receiving, listening, measuring, interpreting, understanding. On Earth, we often think of exploration as movement. A ship reaches an unknown shore. A climber reaches a mountain summit. A spacecraft reaches another world. But science has created another kind of exploration. A telescope can explore places no human body could safely visit. A detector can reveal particles too small to see. An instrument can listen for signals that began their journey long before the instrument existed. Our reach through knowledge can therefore extend much farther than our physical reach. And this becomes especially important when we return to the problem of cosmic horizons. Some galaxies may eventually disappear beyond our ability to establish a future connection. Some regions may be forever inaccessible to physical travel. But for as long as their light reaches us, we can study them, we can map them, we can measure them, we can learn something about their histories. We can reconstruct the conditions of a universe that existed long before humanity. In that sense, knowledge can cross boundaries that bodies cannot. This does not mean science has defeated the laws of physics. Quite the opposite. It is because we understand those laws that we know what the light is telling us. We know that the photons have traveled for an enormous span of time. We know that their information is delayed. We know that the galaxy we observe today has continued evolving after the light we see left it. We are not looking at a live broadcast. We are receiving an ancient transmission. And yet that ancient transmission can still transform our understanding of the universe. There is something deeply beautiful about that. Imagine a galaxy so distant that no human being could ever stand there. Imagine a civilization that might remain forever beyond our physical reach, and yet, one night, its ancient light enters a telescope on Earth. A detector records it, a computer processes it, a scientist studies the pattern, and eventually, a human mind understands something about that distant world. The body never went there, but the human mind did, in another sense. It traveled through information, it traveled through time, it followed the light backward toward the story of its source. And perhaps this is the closest thing the universe gives us to a different kind of travel. Not crossing the distance physically, but crossing it intellectually. A galaxy can remain millions or billions of light years away. The distance remains, the laws of physics remain, the horizon remains, but our understanding grows, and as our understanding grows, the universe becomes, in a curious way, less unknown. There is also something especially precious about the era in which we live. The universe is expanding. Distant galaxies are becoming increasingly separated. Over immense stretches of future time, some galaxies will become harder or impossible for distant observers to see. Some will eventually lie beyond the reach of new light. The night sky available to a far future civilization may be very different from the sky available to us. There may be fewer visible galaxies, fewer obvious clues about the universe beyond our local region, and that means our present cosmic view is something of a gift. We live at a time when the universe still reveals an enormous amount of its history to us. We can look outward and see ancient galaxies. We can trace the structure of the cosmic web. We can study the expansion of space. We can observe the remnants of an early universe. We can piece together a story that began billions of years before our species appeared. And we can do all of this while sitting quietly on one small planet. We do not have to leave Earth to begin. We only have to look. Perhaps that is the strange answer hidden inside the question of intergalactic travel. Maybe humanity's reach should not be measured only by the places our spacecraft can visit. Maybe it should also be measured by the distances from which we can receive information. A spacecraft can carry a human being across space. Light can carry the universe into the human mind. And for some destinations, that second journey may be the only one nature allows. Which leaves us with one final question. If we may never physically reach many of the galaxies we can see, what does it really mean to explore the universe? Perhaps the answer is quieter than we expected. Perhaps exploration does not always end with arrival. Sometimes it ends with understanding. Perhaps by now, the question has changed. At the beginning of our journey, we asked whether humanity would ever reach another galaxy. It sounded like an engineering problem. Perhaps one day, we will build a powerful enough spacecraft. Perhaps we will discover a new propulsion system. Perhaps we will learn how to travel at an extraordinary fraction of the speed of light. Perhaps future generations will build enormous ships capable of carrying entire communities across the darkness. And perhaps some of those things will happen. Science has surprised us before. The universe has repeatedly shown humanity that nature is stranger than our first expectations. But as we have followed the distance between galaxies, something has gradually become clearer. There are several different barriers between us and another galaxy. Some are technological. Some are biological. Some are social. Some are temporal. And some may be written into the structure of the universe itself. The first barrier is simply distance. Andromeda, our nearest major galactic neighbor, is about 2.5 million light-years away. That means light needs roughly 2.5 million years to cross the space between us. A spacecraft moving much more slowly than light would require far longer. Even a vehicle traveling at a substantial fraction of light speed would face a journey that, from Earth's perspective, could span enormous periods of time. And then there is the problem of the spacecraft itself. A machine built by humans would need to survive the journey. Its materials would need to remain reliable. Its energy systems would need to continue operating. Its computers and sensors would need to remain functional. If people were aboard, they would need food, water, radiation protection, medical systems, living space, and some way to maintain a functioning society. A generation ship might solve one problem by allowing descendants of the original travelers to continue the mission. But it creates another. A society born aboard a spacecraft would develop its own culture, its own traditions, its own ideas about the destination. The original mission might become a story passed down through generations. Perhaps the people who eventually arrive would have almost nothing in common with the people who launched the ship. The journey would not simply carry passengers, it would transform them. Then there is speed. The laws of relativity allow massive objects to approach the speed of light, but not simply reach it. The closer a massive spacecraft gets to that limit, the more difficult further acceleration becomes. The energy requirements grow enormously. So the speed of light is not merely a number on a cosmic speedometer. It is part of the architecture of physical reality. And yet relativity gives us one remarkable gift: time dilation. A traveler moving extremely close to the speed of light can experience much less elapsed time than someone who remains on Earth. For the traveler, a distant journey can become much shorter in terms of personal experience. But this does not mean the universe has become smaller. It does not mean the destination has moved closer. And it certainly does not allow a massive spacecraft to simply outrun light. The traveler may experience less time. Earth may experience much more. The difference can be profound. A traveler could leave one civilization and return to a world that has become almost unrecognizable. So, even if relativity helps with the traveler's personal experience of time, it does not solve every human problem associated with intergalactic travel. In some ways, it creates a new one. What does it mean to arrive somewhere when everyone you once knew has become part of history? And while we are considering these possibilities, the universe itself continues to evolve. Space expands. On the largest scales, distant galaxies become increasingly separated. Dark matter helps shape the great structures of the cosmos through gravity. Dark energy is associated with the accelerating expansion of the universe. Galaxies gather into clusters and filaments. Between them lie enormous cosmic voids. The universe is not a static backdrop. It is an evolving landscape. And that evolution creates another kind of limit. A galaxy may be visible to us because ancient light from it is still arriving. We can observe it. We can study it. We can measure its light. But that does not necessarily mean that a spacecraft launched today could ever reach it. Some regions of the universe can become causally inaccessible because of the combined effects of cosmic expansion and the finite speed of light. This may be the deepest obstacle of all. A technological obstacle says, "We do not yet know how." A cosmological obstacle may say, "There may never be a way." Those are very different statements. And perhaps this is the point where we should stop thinking of the universe as a collection of destinations waiting for human visitors. Perhaps the universe is not a map designed for us to cross. Perhaps it is something we are meant to observe, understand, and slowly come to know. This does not make exploration less meaningful. It may make it more meaningful. Think about what humanity has already accomplished without physically visiting another galaxy. We have measured the light arriving from distant galaxies. We have learned that stars contain elements found on Earth. We have watched galaxies forming stars. We have observed galaxies interacting with one another. We have mapped enormous cosmic structures. We have studied the expansion of the universe. We have looked so far into space that we have also looked billions of years into the past. All of this happened while humanity remained on one small planet. The body stayed home, the mind traveled, and perhaps that is one of the most extraordinary features of intelligence. A human being can sit beneath a quiet night sky and think about something millions or billions of light years away. You do not need to touch the galaxy to understand something about it. You do not need to stand beneath its stars. You do not need to breathe its air. You do not even need to send a spacecraft. Light has already crossed the distance. It arrives carrying traces of the place from which it came, and our instruments can turn those traces into knowledge. In that sense, astronomy gives humanity another kind of spacecraft, not a machine, an idea, a telescope, a detector, a mathematical model, a human mind capable of connecting evidence across enormous stretches of time and space. This kind of exploration is slower in one sense. It does not give us the sensation of arrival, but it can reach places our bodies may never reach. And perhaps that is enough. Perhaps the universe does not require us to physically stand everywhere before we can call ourselves explorers. After all, explorers on Earth have always depended on more than their feet. They used maps, they used stars, they used instruments, they used stories and observations passed from one generation to another. Astronomy continues that tradition on a cosmic scale. The map is larger. The distances are almost incomprehensible. The travelers are often photons rather than people. But the basic human impulse remains the same: to look beyond the horizon, to wonder what is there, to gather evidence, to ask better questions, and to accept that some answers may remain forever beyond our reach. Perhaps one day humanity will send probes toward another galaxy. Perhaps some distant civilization will discover a way of traveling that we cannot yet imagine. Perhaps there are physical possibilities hidden inside the laws of nature that we have not yet understood. Science should leave room for discovery. We should be careful not to turn today's limitations into absolute statements about every possible future technology. But we can also be honest about what the universe currently tells us. The distances are enormous. The speed of light is finite. Massive objects cannot simply reach that speed according to our current understanding of relativity. Time dilation changes the traveler's experience without erasing the cosmic distance. The universe is expanding, and some regions may eventually lie beyond our causal reach. These are not merely inconveniences. They are fundamental features of the cosmos. So will humanity ever reach another galaxy? We do not know with absolute certainty. But if we mean physically carrying human beings across millions of light years, the obstacles are profound. The journey may be technically possible in some distant future, or it may remain beyond our practical abilities forever. And there may be galaxies that no civilization in our region of the universe could ever reach, no matter how advanced it became. Yet there is something strangely comforting about that uncertainty, because perhaps we have been asking the question in the wrong way. Maybe the purpose of exploring the universe is not to conquer every distance. Maybe it is to understand what those distances mean, to look at a galaxy 2.5 million light-years away and realize that its light began traveling before human civilization had taken its modern shape. To understand that every distant image is also an image of the past. To realize that the universe contains horizons we cannot cross. And still, despite those boundaries, to keep looking. There is something deeply human about that. We know we cannot hold the entire universe in our hands, but we can learn its patterns. We can listen to its ancient light. We can measure the quiet movement of galaxies. We can study the invisible structures shaped by gravity. We can trace the history of stars. We can reconstruct pieces of cosmic history from photons that have traveled longer than our species has existed. Perhaps this is our form of intergalactic travel, not a spacecraft crossing the darkness, but knowledge crossing the distance, not a human body standing beneath another galaxy's stars, but a human mind understanding something about them. And perhaps, for now, that is enough. Because tonight, when you look up at the sky, remember that it is not a ceiling, it is depth, it is time, it is history. Every point of light is part of a much larger story. Some of those lights are nearby, some are ancient, some belong to galaxies so distant that their light began traveling millions or billions of years ago. And some may represent places that humanity will never physically visit. but they are still there, still shining, still sending their ancient messages through the darkness. And perhaps the greatest wonder is not that we may someday cross those distances. Perhaps the wonder is that we can understand them at all. You can remain here, on this small world, beneath the quiet night sky, and still ask questions about galaxies millions of light years away. You can wonder how they formed, how their stars live and die, how their structures evolve, how the universe itself changes around them. And slowly, patiently, through light and observation, you can begin to understand. The universe may have limits, our bodies may have limits, our spacecraft may have limits, but curiosity has a remarkable way of reaching beyond them. So perhaps, somewhere in the distant future, humanity will build a vessel capable of crossing a gulf that today seems impossible. Perhaps generations will live beneath unfamiliar stars. Perhaps one day, a human being will truly stand in another galaxy and look back toward the distant place called Earth. Or perhaps that day will never come. Perhaps the galaxies will remain where they are, separated by immense stretches of space and time. And perhaps we will continue to explore them in the only way the universe currently allows, by watching, by listening, by learning. There is no need to rush. The light has already begun its journey. It has been traveling quietly for millions of years, and tonight, some of it has reached you. So as you rest beneath the sky, you can let that thought become smaller and softer. You are here, the stars are there. Between you and them is an enormous universe. Some distances can be crossed, some may never be, and perhaps that is not a failure. Perhaps the universe does not ask us to reach every shore. Perhaps it simply invites us to look across the darkness and wonder, to understand a little more, to remain curious, and, for a moment, to feel very small beneath something unimaginably large. The galaxies will continue to drift, the stars will continue to shine, light will continue crossing the quiet spaces between them. And somewhere, far beyond the reach of any human spacecraft we can build today, another ancient photon may already be on its way, carrying a story, carrying a trace of a distant world, carrying a small piece of the universe toward us. And perhaps that is the journey we were always meant to make, not necessarily the journey of the body, but the journey of understanding. So, as you begin to let the night grow quieter around you, you can leave the galaxies where they are. You do not need to reach them tonight. You only need to know that they are there, millions of light years away. Ancient light moving gently through the darkness. A universe still expanding, still changing, still carrying its stories toward anyone willing to look. And if you are already beginning to drift towards sleep, you can let those distant galaxies remain in the background of your thoughts. No engines, no countdowns, no destination that needs to be reached. Only the quiet sky above you, and the soft realization that even from this small place, you are able to wonder about the whole universe. Good night, and may you rest peacefully beneath the distant light of the galaxies.